floor is yours.
Thank you, thank you. Very pleased to be here. Is this working? The control room, yeah, thank you. Perfect. I'm very pleased to be here. I study in the US. I absolutely love the US. I haven't been here for a while because of the pandemic. I'm delighted to be invited. I'm delighted that Smoldering is part of the program. If it was not me talking about Smoldering, that is already amazing. It doesn't happen often at all, so it must be celebrated. I'll tell you in the next hour and a half why. So I'm going to be talking about smoldering combustion. I'm going to be telling you what it is, why it's important, or why I think it's important. Let's see if I can convince you. And what are the ignition process, the spread process, and the emissions. Hopefully I will have time for some talks. Before I start, I'm going to do like Sarah. I'm going to introduce something that is not strictly what Arnaud has asked me to present, but I cannot avoid bringing this message to you. As we speak, it's fire season in the northern hemisphere, and Canada is in serious trouble. In this particular case, every year is only one country is in trouble. This particular moment is Canada. So we are facing some concerns. Different countries at different times are facing concerns. You are the next generation. My generation is already shutting down. We still have a few more years to go. You are the next generation. What you are going to be facing is even harder and more complex. And people, citizens and authorities are going to ask you questions that you need to answer much faster and much better than us. And we leave you all the mess behind that you have to integrate. But what we have is we have citizens that have goals of sustainability. We all want to live in a beautiful planet with in different cities that are sustainable. We wanted the air to be clean because it's such an important thing. I'm from London. Clean air is such an essential thing. And we also want our people to be safe. And there is a premise to solve all these problems. All these three goals and fire is actually hurting these three goals. We want to solve these three goals. And the premise of this summer school, which is not explicitly said, is implied. So just make sure that we understand that, is that by understanding wildfire science, we can address these goals better. It's not the only way we can address these three goals. Some people might address these three goals without absolutely nothing about wildfire. That's why they're not here in this room today. But in the premise of this course is that if we do wildfires, we can address it better. Because, and there is this beautiful quote from a firefighter in the UK, he said, it's at the top. He said, you can read it without the Spanish accent. He said that if we understand the problem, we can manage it. If we do not understand it, we can only fight it. What is Canada doing right now? Canada, she or he is fighting because it is way too late to manage. The only thing that we can do is fight it. And if you don't fight it because you realize it's very expensive and at the end it's not going to do anything, then there will be likely riots in the country, right? So what we want to do with wildfire science, each of the speakers today and all of you are doing in the networking, is we are making sure that we have better actions in our forest to manage the forest. This was a big topic for Sarah today, rightly so. We will have to fight. There is a time to fight. Of course, as engineers, we understand that there is a time to fight, but that's the last thing you want to do. You want to minimize the fight, not maximize it. And also, we want to protect our communities. As engineers, we obviously understand this. These three goals are very important to us explicitly. As a community dealing with a big problem, we are fragmented in our own tribes. It is actually expected to have our own tribes. It's actually even good to be in our own tribes. For example, my tribe is a tribe of people with a Spanish accent that are engineers, that love heat transfer and come from a combustion background. Right? This is what I bring into in the wildfire community. That's my tribe. And I love my tribe. Of course, I love my tribe. But I also recognize other tribes, and I work with them, and I listen to them. And together, we integrate the tribes, and we come out as a community. So there is people who love talking about the community, and they don't care about the rest. That's fine. That's a tribe itself, right? There is people who love fighting fires, and they don't want to know anything about it. That's fine. And there is people who only care about the forest. If you go to a conference in fire ecology, Sarah today brought fire ecology here, such an important thing, to talk about fire ecology and a bunch of engineers, because we are not taught this normally. If you go to a fire ecology conference, not often you will have people talk about flame spread theories, right? They will just show you fires go faster when there is wind. Next, and then we'll spend time about fire ecology. So we are tribe. We need to integrate. So we are doing science. We're doing contributions to the state of the art. And we create new knowledge. And as you only create new knowledge, we are all creating new knowledge. We only create new knowledge. That's really good. We fragment the state of the art. It means that we actually create a mess of little pieces that are left behind. So if there is one thing that I want you to consider doing in your careers, which I try to do in mine, and I try to tell this to our students, is go around also, go behind and try to integrate what the others did before us, what the others are doing at the same time as us, and integrate that with your own bit. Because the bit itself is amazing. The bit itself integrated with the rest is incredibly good. And the other thing that is belong to the tribes is the scale. So right now, Canada is burning. I can guarantee that there is only one thing that the media cares about, satellites, right? Because you have these amazing views of the satellites and maybe some of the images taken for the firefighters. I'm an engineer, right? I actually did the PhD at the same time as Sarah. So I love experiments in the lab at the scale that is next to you, right? I don't go often to the forest. So I love in reality also that scale, the scale that is very close to the flame. They're so small sometimes they look laminar to us. You know, but you can actually go a little bit further away at the level of a watchtower, the firefighter watching this on a hill, and you are getting further away in the scale. And then you can actually maybe see this from a helicopter or a drone, which is really cool. Or maybe for an airplane. Or actually you might be looking to this as a satellite. So wildfires and scientists interrogating and trying to understand wildfires, we bring scales as part of our tribe. No one single tribe can handle the problem by their own. And it is very important to embrace the scales, okay, and make sure that all of them are integrated and they are trying to understand the problem. And I say this because I go to conferences where they only do satellites. It's incredible. Or you go to the Combustion Institute and we only do little flames over here, right? And in reality, it's like there is this massive gap that all of us have to populate, listen to each other, talk to each other, and integrate. So now I'm going to tell you about smoldering. The work that I'm going to present to you is things I've been doing most of my life, trying to integrate the literature of what we do with the rest of others. And obviously it would not have happened if it were not for the students and the postdocs and colleagues that have been working with me. Some of the bits that I'm going to show you today have already been written. And in particular, there is one chapter in the handbook of our protection engineers that talks about smoldering. Smoldering in general, in the built environment, you're all sitting on foam that loves to smolder. You're safe today in this department in particular. And then there is another chapter specifically on wildfires, which maybe brings more into what I'm addressing today. Because I'm going to be talking about smoldering in wildfires, not just smoldering in the built environment. So, usually I don't show this slide this early. I leave it towards the end, but with you it's different because you've already been seeing a lot of flames and people have mentioned smoldering. This is what we're talking about. In reality, there are two big types of combustion, and the two of them are present in wildfires. One of them is the super famous one, is flames, and the other one is the one that doesn't exist, because it's not even a fire, it's just smoking. It's actually called smoldering. Smoldering combustion and flaming combustion, the two of them are very different. The two of them are process of combustion, and the two of them are very important. Flames, tantalizing and very scary, and they move very fast, and they create most of the fire severity, in particular for safety. They have plumes that are very buoyant. They are darker in color because they have soot. You have a talk on soot today. And because it's very buoyant, it goes upwards and actually can go up into the atmosphere. But you also have the smoldering, which is the soil itself or thick fuels. We're going to look into this, not just the soil, but the thick fuels are burning. The smoke is not buoyant. It's at the mercy of the wind or the entrainment of the flames nearby or whatever the atmosphere wants to do. It doesn't have a will of its own because it's not very buoyant. It just raises up a little bit. And it's not as dark. It has no soot. It has particle matter, but it's all about particles of organic material. And it is extremely toxic because it's in complete combustion. So if this is toxic, multiply that by about 100, because this is actually fuel itself that is released into the atmosphere in the gas phase. So I am going to be talking about this, and I'm going to be talking very little about this, right? And Sarah talked about this, rightly so, she's an expert in the topic. And yesterday you had a little bit of mention of all the themes. So since 2003, about 2003, before I finished my PhD, I became convinced, and since then I have not changed my mind, that smoldering is an essential part of wildfires. Not just that it's fascinating and something that I have a lot of fun with, but I really believe professionally that it's essential to understand wildfires. It's not just an add-on. I think flames are still central, but close to that central pitch, it is the role of smoldering. And I have an hour left to try to convince you about this. So the first one is we recognize three types of fires. Sarah has told you this, right? Crown, surface, and grounds. Smoldering. Ground fires, it's not only about smoldering ground fires, but ground fires really like to smolder. It is their preferred mode of burning. It's not the only one, but it's their preferred one. And obviously, they will not exist. Smoldering doesn't exist by itself. It exists combined with flaming, but this is the one that really likes. So when we talk about ground fires, one of the 3 types of wildfires, we are talking about a smoldering. Very few people will mention this word, the word smoldering, when they tell you about this. Types of fuels. Sarah has already alluded to this, such an important thing, right? We say there are thin fuels, there are thick fuels. Depending on the country where you are, they say thin is X millimeters, but in reality in Canada it doesn't matter. And if it's thermally thin or is based on a non-dimensional number, we recognize that the thickness of the fuel dramatically changes its response to fire, right? Why? Because if it's thin, like leaves, needles, grass, twigs, and the very top of the surface layer, they do everything fast. They are able to lose water fast. They are able to heat up fast. They are able to ignite fast. They are able to spread the fire, right? And this is fuels that love flames. They can smolder as well, but they love flames, right? And then you have the fuels that are coarse, that are thick, the ones that everything is slow. And the thicker they are, even slower, right? They dry slowly, they heat up slowly, they burn slowly. These fuels, they can also flame, but they love smoldering. So of the 2 types that exist, there is one type that loves smoldering, and the other one can also smolder, loves flaming. And in reality, you don't have one or the other, you have an in-between, right? Reality is very complex in reality. There is a bunch of fuels in the middle that actually can flame and smoldering, and they actually do flame and smoldering, maybe at different times with the course of a wildfire. And then we have the 3 main phenomena that talks about smoldering. These 3 main phenomena is pit fires, something that I've been doing for a very long time, so you will see a lot of pit fires today. Pit fires is when the soil itself is rich in organic matter, so it's rich in carbon. It's a natural fuel, and it is meant to be either really wet or really cold, and fire doesn't like either of the 2 of them. But when it is not wet and it is not cold for whatever the reasons, climate change or otherwise, they become extremely flammable. So they go from zero flammability, so to speak, of they don't want to burn, they don't want to ignite, to suddenly be really easy to ignite, burn like crazy, smoldering-wise, and it's very difficult to suppress. So they have this dual behavior. We also have residual burning. This is the one that I've been addressing the most in my career, because even the name is pejorative. It's residual. It's like, no, it's not even burning, Guillermo, it's just smoking, right? I mean, the amount of times that people all around the world in different languages have told me, but that's not a fire, it's just smoking. It's incredible, right? So this, actually, Sarah had today even better photos than I did, but this one we use. So this is a flaming fire. You see the flames. Where is the smoke coming from? The smoke that you visually see today, it is not coming from the flames. The smoke is coming from what happens afterwards in the flames. And you don't see it, it's not glowing. It is a smoldering. It is a smoldering combustion over here. Most of the smoke actually is coming from the smoldering. The smoldering was initiated by the flames. It's a transition from flaming to smoldering, an absolutely fascinating topic of science. And actually, most of the fuel, when this fire passes by, most of the fuel that is being consumed per unit area, it is not because of the flames, it is actually because of the smoldering. And for how long is this going to smolder? It could be from 15 minutes to 3 weeks. It depends on the conditions of the fire, right? Now, is this a fire? 100% it is a fire. Is this a flame? No, it's not. So it's not, no, so it is part of wildfires, one of the essential parts of wildfires, residual burning. It's not smoking, it's not burning, it's just smoking. And there are firebrands, another one I find it fascinating. Firebrands is a big, big topic of this field of fire science, and we engineers love firebrands. Such a fascinating topic, right? These burning beads that are flying, aerodynamics, engineers. This is the Department of Fire Protection Engineering here in Maryland works a lot with aeronautical engineers. And then they land and they accumulate and they burn, and it's absolutely fascinating. Well, they are smoldering. They are smoldering, the particular type of smoldering that is very strong because it has a lot of wind. They are glowing. So you turn the sun off and you can take these incredible photos of the embers, the firebrands smoldering. Some of them are flaming, some of them, in particular when they land, the smoldering transitions to flaming, right? So we say, oh, the ember was flaming. Well, actually, the ember was not flaming probably when it was flying. It was actually glowing or smoldering. And when it landed, it transitioned to flaming of itself or the nearby fuels. So that, to me, obviously, it is a smoldering process. I'll be addressing a little bit the topic. So what does it look like in the lab? So I've been doing experiments with my group, and I've been doing models with my group. We put it together, and we've done even field experiments, which is a lot of fun. If you're an engineer, we don't do field trips. We are not trained to do field trips. I always worry that something is going to happen to us in the jungles. But we survive, and I can tell you it's fascinating. And I envy a lot of geoscientists that they do field trips at the university level. So this is how it looks in the lab. This is a tray of about 20 by 20 centimeters. We are looking at it from the top. It's accelerated 100 times, 600 times. This is the visual. This is the infrared. I'm going to show you now again. We ignite on purpose. We're really good now at igniting peat. It's peat. It's very dry in particular. You can see it's very light brown. And what you can see is that visually it's not burning. It's just smoking. 800 times. You have you need a lot of patience for these experiments, right? You ignite, and a supervisor like me stays in the lab only fractions of a half an hour every few months, right? So within half an hour, the fire has not moved. Literally, you are there with the student. It's like, what is this? No, this is my experiment. Like, it's not moving, right? But the student is there 5 hours, right? The students see this, right? So we accelerate it, and you can see what is happening. So it's deceiving. At the time scale of the span of a person, these fires are not very interesting. But I'll show you later on the dynamics of what it does. Interesting enough is the brown is the char, because all biomass chars. Chars is absolutely essential, as you can see, for smoldering. You can have the white of the ash. It's very important in the smoldering to see ash. Flaming, you don't see many ash, because actually it's smoldering that produces the ash. And the infrared, you can see how the process is propagating. So it is low temperature. It has a range of temperatures. For example, if it's glowing, we're talking about somehow 900 Celsius, maybe 1,000 Celsius if it's glowing. But the smoldering only glows in very specific circumstances. And as I say, the glowing requires having eyes, right? It's a definition of visual eye. Close your eyes. Is it burning? It's like, I don't know, because I'm not looking at it, so I don't know if it's burning. It's like, well, it is burning. But you call it glowing, which is something that we see with our eyes, but scientists can refer to fire phenomena without having to use our eyes, right? The heat of combustion is very low. It's about a third or even lower than the heat of combustion with flames. Flames is really, ideal combustion has a heat of combustion with an efficiency close to 1. This is what happens in engines. Wildfires, that drops tremendously to maybe 80%. Smoldering drops it even more to maybe 1/3, because it is not good at extracting all the thermal energy that is possible from the chemistry. It does enough to self-sustain, enough to create havoc, enough to destroy and to harm, but it releases a lot of the chemical energy in the gases, so it's not very good at that. And all these, the two combinations, means that these fires move very slowly. They creep. We're talking about millimeters per minute. So the definition as a combustion scientist is that smoldering is a flameless combustion. Don't look for the flame. It is not a gas phase phenomena. It's a heterogeneous phenomena where there is a slow process of propagation at low temperature, and typically happens in materials that have some level of porosity. All biomass invented by nature is porous, and all biomass invented by nature chars. And these are two fundamental properties, physical and chemical, of fuels that could smolder. That they are porous and they char. Why is this important? For two reasons. So the chemistry that is involved in the smoldering is what we call, at the chemistry level, heterogeneous. Heterogeneous because it involves two phases. One is the oxygen. Obviously, smoldering consumes oxygen. Once upon a time, people thought that smoldering was this secret combustion mode that didn't need oxygen. It does need oxygen, but not at the rate as the flaming fire, because it is much higher heat release rate. So the oxygen is in the gas phase, and then it approaches the solid that is burning, which is going to be the char, not the fuel itself, but the char is what loves to smolder. Char is in the solid phase. The oxygen gets absorbed on the surface of the char, and on the surface of the char, which is a solid phase phenomena, it oxidizes and it releases the gases back into the smoke as a smoke, and it releases the heat. So that is heterogeneous because it involves two phases, gas and a solid. We're going to address that, what happens in a flame. Flame is an homogeneous chemistry because both the pyrrolysate and the air, when they mix and they burn, are both of them in the gas phase. Typical natural fuels that love to smolder is all of them invented by nature. that are combustible, so biomass, for example, wood, peat, litter, coal, even fossil ones. And we humans have come out also with a few synthetic fuels that love to smolder, in particular foams, polymeric foams, not all of them, the ones that have a tendency to char. And because they are foams, they have a porosity. So the char bit is important because char is concentrated carbon. Carbon, as you know, loves to, if it can, to recombine with oxygen and release a significant amount of energy. Is the hydrocarbon characteristic of the chemistry on the planet Earth. And because it's porous, it is going to create a lot of surface area within a given volume. So you have a volume. If it's not porous, if you have a block of material that is not porous, well, it's not very solid, is it? This one either. Okay. It doesn't have much of a surface area. It only has the surface of the solid. But if it's porous like this, okay, now you have in the same volume an incredible amount of surface, the surface of the pores inside. So you multiply the surface area by 1,000 by the fact that it's porous. And smoldering happens on the surface of the char, on the surface of the porous media. So it loves to have porosity. And the more porosity it has, the more it will actually smolder. And the less porous, for example, wood, has natural porosity, but not high. So wood can smolder, definitely solid wood, as Harry knows. But maybe it will not smolder as much as the soil when it's dry in peat. And the fact that it's porous, it means that the two most important mechanisms of smoldering can be maximized inside the porous media. These are, smoldering is always limited by the supply of oxygen. It has enough to continue, but if you give it more, if you increase the oxygen supply, smoldering will take it. It's always limited by the oxygen supply. And at the same time, it's very sensitive because it's not a powerful mode of combustion. It's very sensitive to heat losses. So it shies, it literally shies. The definition is if you were to see the smoldering front, it shies away from heat losses because it will quench it. So it goes deep into the porous media. It can access the porous media, and it is away now from the surface, from the wind, and from the radiations to the environment. So it loves porous media because it feels less shy, so it goes inside. And because it's porous, and it's not in a hurry for the oxygen supply, the oxygen can reach from the front, from the back, and from other sides can reach into it. So porous media, it is, for a reason, based on the fundamentals of the chemistry and the physics of the smoldering, why it can happen. Now, when we put all this together, this is fascinating. Guillermo, you're having a lot of fun watching all these smoldering things. Why should we care? Well, from the fundamental point of view is because it is very easy to ignite a smoldering fuel. Very easy. If the fuel can actually sustain smoldering, it is much easier to start smoldering than actually is to flaming. And we can measure this in the lab. For example, the ignition source that you need by radiation, if the fuel is able to sustain smoldering and flaming, you need about half of the radiation heat flux to start smoldering, and you will need twice that amount of radiation to do it flaming. If you want to ignite at very low temperatures, you can't. You cannot initiate a flaming combustion at low temperatures. You need at least the ignition temperature of the fuel, which we're talking about 300, or you need to somehow to get at the temperature of the flame. With the smoldering, we have the process of self-heating ignition. I don't know if you have heard about this absolutely fascinating topic, which got a Nobel Prize in 1956. Self-heating ignition, which explains ignition fundamentals of combustion science, it also can happen in smoldering. And it means that there is a process that is not in a hurry, it might actually take weeks, if not even months, where the process of smoldering starts in the inside of a porous fuel without any external event, at ambient temperature, literally. Now, typically is sensitive to temperature of the environment. So if you are in a drier, hotter place, you will see more self-heating ignition than if you are in the Arctic and it's very wet. But self-heating ignition, it is possible, and it tells you, it starts a smoldering process. So smoldering is even possible at ambient temperatures. It's not frequent, can be considered a natural phenomena, and it's very, very difficult to investigate. If you're doing forensics and someone says there is a fire, 200 acres have burned, we think it started by self-heating. All the evidence have been burned by the fire. So then it's very difficult to actually pinpoint if a fire had started by self-heating because all the evidence disappears in the process. But self-heating, it is possible. And then once it's burning, and we want to suppress it, it's actually much harder to suppress than flaming. For example, the amount of water that you need is in the order of half. You need 1.5 times up to 2 times more water per mass of fuel that is involved. We do this in the experiments, as I'll show you later on today. If you want to smother it, if you want to actually lower the oxygen concentration, as sometimes we do in fire protection, to stop the process, you have to go much lower in concentration of oxygen if it's smoldering than if it's flaming. You can actually knock out a flame in about 16% concentration of oxygen. So you go from 21 to 16, you knock off the flame. The flame cannot sustain itself. But smoldering can go up to 10%. And I have experiments where smoldering was going at 2%, which obviously doesn't have many relationships to the natural environment now. But once upon a time, millions of years ago, the planet Earth didn't have an oxygen atmosphere of 21%. It had an oxygen atmosphere of much lower numbers, and still wildfires were happening. So I can tell you already, fascinating, right? So if you go below 16, you cannot have wildfires. But the historical record, the fossil record, shows wildfires when the oxygen concentration was lower than 16. Maybe the wildfires were of a different type to the ones that we see in the news today. If you want to smother it, you knock the flame off, you can blow the flame, and it will cool down, and it will be, that's it. And within seconds, within minutes, you just dealt with the process. If you want to do that with a smoldering, you will have to withhold the oxygen concentration at low numbers for weeks, because the amount of fuel that is involved is much larger. So I say, when I was looking into our data and our experiments, if this is the easiest to ignite in this planet, and is the most difficult to suppress, it is obvious that nature has something going on with the smoldering. And I call it the most persistent type of combustion in this planet. I don't know how this will happen in Mars, they don't have vegetation, or in different planets and ecosystems, but in planet Earth, there is something going on with the smoldering, right? And that will not surprise us then that the oldest fire, not wildfire I would say, but the oldest fire that has been burning continuously that we know about, it is in Australia, and it's actually a national park. It used to be a sacred site for the Aboriginals in Australia. That's me, it's safe, don't worry. I did the risk assessment, I was in a safe place. And even the British thought it was a volcano when they arrived, right? This is next to Sydney. So there's this article in 1828 where they thought, breakthrough in science, a volcano where there is no volcanic activity. So the scientists, the volcanologists, went and they thought, but a volcano is just a fire, and they left. I promise, they thought that if it was a volcano, it was really cool, but if it was a fire, who cares? And they left, right? So we are happy to say the fire continues. So those of you in Australia, you can go. It's about 3 hours from Sydney. It's still burning. It moves about 1 meter per year. This was in 2018. So now it's actually arriving to the end of the cliff. And what is burning is coal. So it's a natural fuel, but it's not vegetation, and it's not a wildfire, okay? And it's burning the coal seam. At least 6,000 years old, because there is people who think that it's 500,000 years old. The evidence have been lost a little bit. So when you go around the world, you see when smoldering made the news. This is actually probably the single most famous smoldering phenomena that we know about. It happened in 1997, although the paper was published in 2006. So we as scientists, me in particular, we didn't learn about this until 2002. When I was doing my PhD there with Sarah, I thought something is going on here when this was published. This is a satellite photo of the smoke that was produced. It's not a plume. It's not that it goes up into the atmosphere and travels around the world. It's that it was spreading at the surface level for weeks and weeks and weeks. These fires lasted for about 3 months in Southeast Asia, mostly in the different islands of Indonesia, but not only. And it led to the first international complaint of transboundary pollution. Australia and China were not happy, and Malaysia were not happy that the Indonesian fires that they could not do anything about, they were actually sending emissions, long-term emissions, not just a plume that goes from the US to Canada for a week. This was there for months. And it was the air that people were breathing, not the air that they were looking at it. It was the air that they were breathing. So it was a big deal. Then there was this fire in 2008. Hopefully the video works. It wants to work. No, you think it's not going to work?
Media not working.
Yeah, this media not working. Fine. 2008, I was, by that time, a young academic at the University of Edinburgh, and this was the biggest fire that happened in North Carolina in the record by that time, and it was actually next to the EPA headquarters. EPA could not care less about smoldering combustion, literally, but they happened to have measurement devices. EPA is really good at measuring air quality. And they had measuring devices next to their offices, and suddenly they thought, we have this amazing health air pollution emergency that happened next to us, and they have some of the best papers that we have in air quality of smoldering, not because they were looking for it, it's because smoldering were looking for EPA, and they found them. So this fire is very interesting. It lasted for about a month. I want to show you the video because you will see the whole landscape. It's from a helicopter. You see the whole landscape burning, not one single flame. Don't look for the flames. Don't turn off the lights. Don't turn them off. You will not see glowing. You will not see flames. It was just burning for about a month. The authorities were very concerned. It's a national, it's an ecosystem that is of natural treasure. So what they did is only the Americans can do this. They reverted rivers. They put thousands of pumps. They re-flooded the peatlands of North Carolina. Very few people can do that. Everybody wishes to do that. There are only 2 cases in the world where this happened. One, North Carolina, the other one, New Zealand, but it was about 100 times smaller. Look what happened at the end of the fire. That's a tree. This tree used to be very happy growing at the surface of the forest, and about a meter, half a meter to a meter of it has disappeared. So what is it? It's in the air of North Carolina. And that's the organic part, the one that can actually be gasified. And the one that cannot be gasified, that's called ash, and it's there. And there was an ash layer of about 20 centimeters, which corresponds to about the ash that will come from a layer of organic soil about this size. So when you look into the amount of fuel that was burned per surface area, this is about 100 to 1,000 times more than what happens when the tree or the foliage or the pine needles burn. And why is this important? Because when you look at the satellite, you only see the 2D projection. You don't see the in-depth. So you see that plume over there? That plume is the same. It's a big plume. But that plume is as big as the ones that you see in California. And they stay there for maybe 2 weeks, and it's dramatic. That plume was there for a month. So you can do the integral, right, of the size as a function of time from t equal to 0 to t end, 1 month. And you can see that the amount of fuel that smoldering burns and releases into the atmosphere is not the same order of magnitude. It's orders of magnitude higher than flaming fires when smoldering happens. This type of smoldering doesn't happen all the time, but when it happens, it's very dramatic. It's not just 2008 in North Carolina. You can see Indonesia, unfortunately, every 3 years. We are due one this year. It's in the news typically what happens in Indonesia, the El Niño, La Niña, anthropogenic drying, it just doesn't matter. Unfortunately, it happens even in Siberia, closer to Europe, Germany, the United Kingdom. I'm going to show you. These are the ones that are so big and so weird. In particular, this one was very weird. It was happening, I think it was close to Moscow. That journalists were asking, what is this? It doesn't have flames. It's weird. What is it? Right? That's when it hits the news. And I want to show you one closer to home. I'm in the UK now. This was a big fire for the UK. You can barely see it in the satellite, but you can see it. And that in the UK already is something, because the fires in the UK are small. So this was not a small fire. This was one of the biggest fires that the country has seen in many years. They're very small. But you can see the drama here unfolding. This is the population, and this is a national treasure. This is an ecosystem. It's the Southernmost Park, right? So they want to protect the moor. They're actually related to the water quality of the area. They want to protect people. Right now is the worst case scenario. Fire is going into the peatlands, and it's going to damage them. And the smoke plume is going into the people where they're smoking. Worst case scenario. It could be the other way around. Probably will be worst, because then the flames are going into the people, and who cares if the smoke is going into the moorlands, right? And that's what the satellite can see. So scientists that do satellites is absolutely a fascinating job. They can see so much at that scale. But they miss this other scale, which this is actually what happened with Dr. New. She went after the fire with a little camera at the scale of a person, right? And she could see these incredible pans of smoldering. This is ash. Typically, when you see ash, smoldering is happening. And this is the char that actually was produced by the flaming. And this is burning. And Stacy was there, I think it was 5 days before. And the firefighters had to stay about a month afterwards, because they could not stop the soil from smoldering. And the damage that it produced to the ecosystem, the peat in particular, there in the UK is very valuable, was dramatic. So the scales matter, right? For example, if you use the satellite, I have professional, healthy discussion, but intense, with satellite people because they cannot see a smoldering. It's not their fault. It's just the smoldering doesn't want to be seen. It happens on the surface at low temperature. It just doesn't want to be seen. Therefore, people in satellites, I don't know how many of you are working in satellites, they don't think smoldering is a thing. It doesn't even smoke. They don't even know where the smoke is coming, right? So I tell them, it's like, you cannot see a smoldering. It's like, prove it to me. I like, okay, well, I have 20 years to go. This is another fire that happened in Spain. I just bring it because I was there. It's a national park, the smallest national park of Europe. It's peatlands. Spain is not meant to have peatlands. It's a very dry place. We are close to the Sahara. But there is these peatlands in the south of Spain. They're absolutely beautiful. This is when I arrived in 2009. It is a desert. I actually call it Mordor because there was actually no life there. It's literally dry. That is peat. That is peatlands, right? Peat is produced when there is vegetation in the excess of water. I was like, where is the water, right? I was actually walking, and they took me there by the cars. And then this is what happens about 6 months later. Nature brought back the water the way it's meant to be. Nature, no humans were involved here. And now the place where I was walking, now I was in a little boat, and it was very melancholic, and it was beautiful, and the birds were there, and they were migrating in the way to Africa, and it was amazing, right? So this is what is meant to happen, and this is why it could happen. It was not just climate change. There is a lot of anthropogenic effects here. It was smoldering, and it's a national park. It's actually UNESCO site protected. They were freaking out, the authorities. What is this thing? It was not even called fire. What is this thing, right? It's not even burning. It's just smoke, they were saying. I want to show you if hopefully it will work. Media again. Oh, no, it's moving, though. Yeah. Okay. Really? Yeah, it is. This video, it was in the TV. This was the moment of fame for smoldering combustion. This is the Spanish TV channel, and they were like literally showing this, like, what is this? Right? Look, it's magic. They say it's burning. We don't see flames. And literally, it is very dramatic. This is a scientist they invited to look into this. So it was extremely dry. It was burning. It was not burning on the surface. I'll show you now what the satellite was able to see. It was burning under because smoldering was shy. It was dry enough, but it was getting enough oxygen, and it was just burning in the atmosphere, in the subsurface. So this is not what a satellite can see. This is what a drone, one of the first uses of infrared technology in a drone with wildfires. This happened in 2009, right? So they took a drone that was actually being used for the vineyards of the south of Spain and said, can you just deroute and go here? But they said there is no vineyards. We know, it's a national park, just do it. It scanned the surface, and you can see all these thermal anomalies. I love infrared. This is what the satellite can see. Where are the fires? Well, I highlighted them for you, right? People are, oh, look, that's a fire. No, that's not. That's people. Actually, that's the visitor center. Oh, look, there's a fire right there. No, actually, that's the agricultural site. So where is the fire? Here, 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 and here. So what do satellites do? When they see this, they say thermal anomalies. Wipe. Shoo. They wipe all the smoldering because it's a thermal anomaly, because smoldering looks like a car or a factory or a building, right? So they are thermal anomalies. They cannot see smoldering. It is not their fault, but maybe recognizing it will be helpful for this. Now, smoldering can be of two types. You've already seen a few of them. It could be that are close to the surface. We call it shallow fires, typically of about a meter. But actually, smoldering can go deeper into the subsurface. It can actually go as deep as the two limiting steps. It can go as deep as the oxygen can get there. And natural fuels actually have cracks in the soil. They're actually complex channel networks by nature in peatlands that allow the oxygen to arrive and the smoke to leave. And until it reaches either the water table, then it will not be able to be there. Or it may actually enter on one side and maybe after some time appear back. I did this sketch with I'm not very good at drawing, with an artist in 2008. And I had a big deal. I was super proud of my drawing. Look, shallow fires, deep fires. Yeah, because it's about the oxygen supply and the heat transfer. I was looking at me, people were, what is this guy talking about? Now it's called zombie fires. And that is really cool, right? So this is an example of science communications. The science itself is amazing. citizens could not care less unless you put it into a set of words that they can relate to. You say smoldering fires can be deep and shallow, they're busy, and with a Spanish accent. You say there are zombie fires, and people are like, what is that? Zombie fire, ooh, what, it was dead, and it's coming back alive, ooh. Journalists, which are the interface with citizens, love the concept of zombie fires, to the point that we have papers. It's good for us, for fire science. We have papers on smoldering, obviously, right? With all the jargon, all the models, all the experiments. If I go to a journalist and said, I have a paper on peat fires or smoldering, they're like, oh yeah, leave it on my desk. And 1 out of 10, they make a press release on it. If I say, and I've done this, I have a paper on zombie fires, tomorrow we call, interview. Literally, 2 days later, there's a whole paper. He has read the paper, he has understood the paper, because it was about zombie fires. The same person, the same journalist, if it's not zombie fires, doesn't read the paper, no article, then citizens don't get to know about the smoldering. So what are zombie fires? Well, since then, we did another sketch, knowing that zombie fire is such an important thing. This is something that is related to the Arctic, which has consequences to what I'm going to say afterwards. This is typically a wildfire with flames. Satellite can see it, flames, right? Either it is extinguished by itself because the rainy season or the cold weather comes or firefighters have been successful. The flames disappear. There is a record that the flames have disappeared. This is very important, okay? And they say the fire has been extinguished. What happens is that the soil, for whatever the reasons, is organic and is flammable. Smoldering starts to move into the soil. And then the colder, so smoldering continues. So there's no more flames. Smoldering continues. Then the cold winter comes, maybe even a layer of snow on top, right? We humans, we live on surface. We are like, there is no way there is absolutely anything happening that is thermally related under this layer of very cold snow. And what happens is that smoldering is able to survive as long as it goes deep to get away from heat losses, as long as it can find enough oxygen, and it's not in a hurry, right? So it lowers its intensity, it lowers its temperature, it lowers its heat release rate, it lowers its reaction rate, but it doesn't extinguish, it doesn't disappear. And it stays there over winter, and then when the snow layer disappears, can get more oxygen, and the temperatures on the surface increase, the smoldering goes up, satellite still cannot see it, but now it ignites flames precisely on the same spot where they were the year before. And they think this is freaky. And they call them zombie fires because they thought it was dead, but it came back alive, right? And they were just trying to relate something like, we are seeing this weird thing. We call it zombie fires, right? And it succeeds. Now there is more people. I can write a proposal saying zombie fires, and my rate of success multiplies by 10. I write exactly the same proposal, but the title says smoldering combustion in natural fuels, and I get a very low rate of success. So why is the Arctic such an important thing for us, and actually relates to all of you in the room? I'm not an expert in this thing, is that we are seeing unprecedented behavior, fire behavior. Unprecedented in the amount and the frequency of bad fires. There is such a thing as good fires. We are not concerned about the unprecedented amount of good fires. We see very little good fires. We see a lot of bad fires because we see that there is an alternation, is a perturbation of the natural fire regime. The natural fire regime is what the forest needs to continue being that ecosystem. If the fire regime in intensity or frequency is reduced or increased, the ecosystem evolves, right? It becomes a different ecosystem, and the fire ecologists care about that. So the question is, why are we seeing all these unprecedented fires? Right now, California definitely. Canada is seeing one. This is the same graph as that I have shown you. The number of fires is relatively the same in a very long term, but there is an increase in the burned scars that we are seeing. Therefore, we are seeing more of the bigger fires. That's not good. It's going to catch more people. That's a bad fire. It is too intense. It might actually become a bad fire. So what is this? And everybody wants to say it's climate change. And all of you, when you are in the bar and you tell anyone that you're doing wildfires, citizens of the world have asked you, oh yeah, we're all going to die because of climate change. And I understand this is what is in their minds, right? We as scientists, we know that climate change has is an issue, not the only one. We know that land change use is an issue. This is what happens in Indonesia, for example. It happens in the Amazon. What used to be virgin, now it's not virgin. Someone has entered. Humans typically, they're changing the land use. They're making agriculture, they're doing plantations, they're extending a road. That changes the natural, that changes the fire regime away from the natural. That creates bad fires, at least for a while. We also have population changes. We have people moving into the wilderness. We love it. In the US in particular, they love it. It's pretty, you can commute, it's inexpensive. And you're bringing homes and humanity to the wilderness. And as it happens in my country, people are leaving the rural areas. They're abandoning the rural areas where they've been for thousands of years, and they go back into the city. The two of them are changes of people. And then we have something that is happening in the US, and a little bit in Australia, and a little bit in Europe, which is fire exclusion, which is something that is very important that Sarah has mentioned. And the question is that all of them, here is a mess, because everything matters. You can move, here is only two of them, here is just, but what is the Arctic? The Arctic is there. The Arctic, no one is changing the land use of the Arctic. There is very little human interest in changing that land use. There is very little people in the Arctic, right? It is very bucolic. And there is no fire exclusion in the Arctic. There is actually, fires in the Arctic are not even fought. They're just watched, because there is absolutely no one that can do anything about them out there. So it becomes a poster child of fire science and climate change, what happens in the Arctic. And that's actually why winter fires and zombie fires is also such an important topic, which is related to smoldering. Because it is, by studying what is happening in the Arctic, we are answering one big pressing question by citizens, right? Away from the complex melee of all the other things that matter. Good. So now about the chemistry. I've already alluded to this. Smoldering combustion is heterogeneous. Smoldering combustion requires pyrolysis. Pyrolysis is such an important equation for us. So the biomass, which is in the solid phase, will be heat up through a heat source. It could be the fire itself, or it could be the ignition source. And it will split into pyrolysate, which are gases, and what is left in the solid, which we call char. So this is the mother, this is the beginning of any combustion process in a wildfire. All wildfires have that step. It can be disclosed, appreciated, studied. Stas Stolerov, for example, loves this step over here, right? Or you might actually not like it and hide it. But it is happening because it has to happen, right? Without that step, there is not a wildfire. And then, if what is oxidizing is the char, as I told you before, is this char is oxidizing with oxygen, char being solid, oxygen being gas, you have heterogeneous chemistry. And it leads to combustion gases, very complex set of combustion gases, and in particular ash, that is smoldering. And flaming is the other one oxidizes. If the pyrolysate, which is in the gas phase, if the pyrolysate oxidizes with oxygen, gas, homogeneous phase chemistry, that would be flame. So combustion by smoldering or flaming has a root, a beginning in pyrolysis, and it's depending on what is the species coming out of pyrolysis that oxidizes that says one or the other. So very important what Stas told you yesterday about pyrolysis. And the two of them love to talk to each other. Not only that they happen next to each other, smoldering and flaming, is that one leads to the other. For example, a classical example of a transition from smoldering to flaming in wildfires is spotting, or arrival of firebrands that then lead to the ignition. When people look into the ember problem or the firebrand problem, they care about flaming ignition. This is by far the single most important one. But they often, when they study, they see that before they see the flames, they see a lot of smoldering, because there is a transition that happens later on. And we also happen to have the transition from flaming to smoldering, the other transition. We saw that is the residual burning. This is the fuel, pine needle nice, with little flames already, with the peaks and troughs. They're propagating in this direction. And what is happening afterwards is smoldering. Who started it? Flaming. There is a transition from flaming to smoldering. Do all the smoldering happens before a flaming? No, they can go either way. There are fires that are only smoldering. I show you a few. There are fires that have zero smoldering. They do exist. And there are fires where the flaming and the smoldering are in the same time and in different places in different order. So how do we know that it is true that the char is what is oxidizing in smoldering? So this is a very cool experiment in the lab The lead author was Rory Haddon. Some of the students are here today. This is the sample of peat in the FPA, famous FPA apparatus. It's being radiated from the top. And this is what happens if you're doing the visual. Looks very boring, it's not burning, right? Well, this is in the visual. In the infrared, you see it is actually, in the infrared, it's glowing, but just because it's emitting radiation. So what Rory did is amazing. What he did is he did a very long experiment of about 2 hours. But he was stopping the experiment very quickly at different times, right, from ignition till the end of the experiment. And he was taking out the sample, he was spreading over the table, and he was very meticulously separating white from black from brown. Brown is the peat that didn't burn, not degrade. Char is the peat that had paralyzed into char, and ash is the char that once upon was. And he tracked the three of them, and he produced this plot, where you can see in red is the char, in blue is the peat, and in black is the mass loss in total, right? And you are tracking the mass that happens in the sample as a function of time. So the first thing that you see is the blue goes down like crazy. The peat disappears, and after about 15 minutes, there is no more peat left in the sample. Is that the end of the fire? Not at all. The fire continues for about an hour longer. But what is burning? Look, the char. The char goes up, and then it goes down. When you see in combustion science something like this behavior that as a species, chemical species, that was not there at the beginning, and it's not there at the end, but it's absolutely essential in the middle, we call it intermediate species. And in combustion science, it's an obsession to look into with lasers for intermediate species. Well, char is the intermediate species of smoldering. It was not there at the beginning, it's not there at the end. It is absolutely essential and is the driver of smoldering combustion. So this experiment is not just a theory of the char should be oxidizing, it is showing actually that char oxidation is what drives smoldering combustion. When we look into the chemistry and we do experiments, we can stay here, right? We could choose to stay here. But unfortunately, for good or for bad, we are also modelers. And modelers need to be able to quantify reaction rates. It's a pain. But you have to, otherwise your models don't have the core of the fire problem, right? You have the reaction rates. So one of the best ways, and I know Stas told you about this yesterday, the best ways to get reaction rates when your fuel is solid is TGA, thermogranularimetric analysis. And this is summarizing, you take a really small piece of the material, and it has to be very small, because if it's very big, it's not TGA, it's an experiment like the ones of Sarah. It has to be very small, thermally thin, homogeneous. You put it in an apparatus, which is extremely sensitive and delicate mass balance, and then you heat it up very slowly at different rates, and then you track how it loses mass. Right? This is a very small sample, and it loses mass, and you have to correct for buoyancy, you have to correct for all these things. You end up with these curves like this. This is the temperature that we have in the TGA. It's ramp, so you start cold, and over the course of an hour or a day, you heat it up more. And what you have in different curves is the reaction rate, the speed of losing mass. Right? So some things are happening. And each of these curves is a different biomass. So for example, in blue is pine needles. There are some global experts here on pine needles. In red is peat from the forest, in black is peat from the moss, and in green is wood, pine wood, tiny little piece of wood, right? And what you see is that it's a mess, but the two of them have two peaks. So chemically speaking, with Stas, we look into this and we say, at least I see two chemical steps, at least. I mean, some of them have multiple steps. At least, let's summarize. What are the chemical steps? Well, one is happening before 80 Celsius, and the other one is happening in the order of about 300 Celsius. And this experiment that I show you and disclose it now was done in the absence of oxygen. I cannot get to the top, but you can see over here. So this mass loss was nitrogen atmosphere, not reactive. This is only pyrolysis. So this is the drying, because in natural fields we always have drying. Sarah has made that point. And this is the true one step of pyrolysis. And then what happens if you do the experiment, but now you allow it to oxidize? In the smoldering, it will oxidize tiny little bit on the surface of the sample, and now you have drying. It's good that you still have drying, because oxygen should not modify the drying step. It's still there. You still have the pyrolysis step. Oh, interesting. And you have a new step. What could this new step that happens after pyrolysis at a higher temperature? That is the oxidation step. So then now you have a way to quantify the peak is the intensity of the reaction rate as a function of temperature. So we call upon Arrhenius. I absolutely love Arrhenius. And you are able to say, well, what is happening in your sample? Well, in your sample, you have water, you have porous media, you have water in the pores, you have water that has become actually hydrostropically attached, you have peat that has organic matter, and you have mineral layer. This is what happens when you have a porous field. And then what could happen to it? Well, it could happen that it dries, or it could happen that actually it pyrolyzes and it oxidizes, and it could happen alpha char and beta char. I love this alpha char. I know you don't know at this point, that's fine. It is alpha char, beta char is not something that can be done in a summer school. It needs to be read. But then we have Arrhenius reaction rate. And if we are able to replicate those plots going up and down for each of the chemical steps, we are able to quantify the importance of each of the steps. The first step is the drying at the top. The next one is the pyrolysis. The second, these two over here are oxidations. And we are able to fit and come out with a exponential factor, activation energy, reaction order. We can even have a stoichiometric coefficient for oxygen concentration. We can actually even get, if we have a thermochemistry, we can actually get a heat of combustion, etc. That is for a five-step chemistry step. It's very complex, but we've done it for 3, we've done it for 5, we've done it even for 9. So now what's your cup of tea? You prefer 9, 5, 3? You're not expressing peat, you probably just want 3, right? To like drying, pyrolysis, and oxidation, that's fine. But who says that that's the right one? It depends on what you want to do. You might actually need to be able to get 5-step. And if you are only doing peat, then you might actually want the 9-step and not being able to talk to anyone else because no one can keep track of what you're saying. So at this point, I'm gonna take a little break and get your questions. So you have questions now for the next 2 minutes in case, and then afterwards I continue. And it gives me a chance to drink. It does. It's a porous media. Porous media has pores. The pores are in the gas phase. I mean, the absence of solid phase is gas phase. They will be filled with something. Probably water vapor, probably nitrogen from the atmosphere. But yes, it has a little bit of air trap. But that air will not last for long. So if it says that air can initiate self-heating and be consumed with a reaction rate, an actual reaction rate of about a week. But then after a week, if it continues, it has to take the air from the outside. It is not enough for self-sustaining. It's enough for self-heating ignition.
You know that smoldering is oxygen limited. If a smoldering fire was exposed to an atmosphere of higher oxygen content or pure oxygen, would it continue to smolder brighter, if that's the right word, or would it transition back to that?
Awesome question. So if you have a smoldering happening already and you increase the oxygen supply, and you can increase that by 2 ways. You can increase the oxygen concentration in the wind that you're bringing into the lab, or you can increase the wind. Okay? Typically, smoldering immediately reacts to this, and it starts to burn faster and hotter. If instead of increasing only the wind, which also increases heat losses, you are only increasing the oxygen concentration, which doesn't affect the heat losses, you might have transition to flaming, which is typically what in Berkeley we were doing. We were having the smoldering, and suddenly 1, 2, 3, we were increasing the oxygen concentration, and boom, we were having transition to flaming. The only thing is in nature, not very often, you change the oxygen concentration. So as scientists, we love changing the oxygen concentration. We literally love it in fire science, in combustion science. But in wildfires, ecologists are looking at you saying, you change the oxygen concentration? We're like, yeah, it's fascinating, right? So then we prefer to change the wind. But if you change the wind, you are bringing oxygen supply, but you're also increasing the heat losses. So you can still have transition to flaming, but now you have the same mechanism is promoting and hindering smoldering. And it becomes fascinating.
When you model smoldering using computation model, how is drying initiated? Because drying was before 400 in the curve. So how do you initiate drying? When do you do?
Great question. You mean how do we simulate, how we computationally simulate drying? The best way that we have found to look into this is we simulate drying as a Arrhenius reaction rate. And some people are like, oh. But because the drying that happens in wildfires is a non-equilibrium process. It's non-equilibrium, this is very important, it's happening in real time. Arrhenius, although fundamentally might not explain it, it works. So Arrhenius got a Nobel Prize for his work, and his work will not be related to drying, but it works. So we do Arrhenius reaction rate, and it works really well for us. But it's true that fundamental level, it is not pure Arrhenius, it has to be something else.
So it is still missing the drying isn't just because of mass concentration difference. Like that is still missing.
Oh, great question. No, yeah. So drying, as we heat transfer people, maybe you're a mechanical engineer as well, or chemical engineers, we understand it as a diffusion process.
Yeah.
It is, but in real time. So it's a non-equilibrium diffusion process. If you don't bring the effect of temperature, you will not be able to capture what is happening. But that's why the Arrhenius works, because although it is not fundamental Arrhenius reaction rate, it behaves as if a chemical process that is extremely sensitive to temperature. And then we adjust it with activation energies and exponential factors.
My question is about the residual burning which follows the flaming spread. Do we know whether this smoldering affects the fluid field of the, or is the main influence just from the flaming combustion?
Awesome. I don't know the question. I've not looked into the question myself, but I can tell you that smoldering, it alters the environment a little bit by consuming the oxygen. It does consume the oxygen, not all of it, but it consumes a significant amount of oxygen. And it is buoyant because it releases heat, and you can see that actually the smoke wants to rise up. It's not a strongly buoyant one, but it's mildly buoyant. That will alter the field, and the bigger the smoldering it is, the bigger that strength will be distributed around so in the lab, this is a very cute little plume that you move the hand and it goes away. But you multiply this by what happens in North Carolina, which is literally multiplying the piece of things that we build in the lab by 1,000,000, and you might end up with a plume that actually has strength. But very few people, with the exception of people in Missoula, talk about this. But if you have a flame, it is so much more buoyant, the strength of buoyancy is so much larger in a flame that it will explain the plume. If the two of them are together, the buoyancy will be explained by the flame.
Actually, that was my question.
Okay.
If the smoldering is enough, the buoyancy from the smoldering is enough to influence, or it's insignificant and we can exclude the buoyancy?
Typically we exclude it, and I think there is a good reason why it's excluded. If you are looking at the smallest scale. If you're looking at the biggest scale, my understanding is that Missoula is asking the question that this might not be negligible anymore, and they have a point. But no one has looked into this with the exception of Missoula. One more question, I continue.
So with zombie fires that are occurring like many, many meters in depth below the peak, would there be sort of any observable smoke plume generated, or would sort of the...
Yeah, great question. I mean, we don't know this with peat, we know this with coal fires, right? So for example, the fire in Australia is burning. It is uncontroversial that it's burning. You will not be able to find the plume. It's not just the satellite. Even myself, I could not see the plume. You just feel warmth, general warmth, but it's not like you can say, the volcano here, right? So there is no plume. The fire, which is right now, as we speak right now, is quite deep. It's about 30 meters deep. Once upon a time, it was about 5 meters deep, and that's when they thought it was a volcano. It was glowing up. Now it's very deep. It is finding a way to expel the smoke through different channels here and there, but it's not like there is one chimney and that's it. What I found, and I love that, is the oxygen has to arrive to the sim, which is 30 meters down. So there are cracks that actually are injecting oxygen inside. And you can see many cracks, tons of cracks in that place. And some of them are suspiciously clean of sun. They're like literally pristine, and they go quite deep. And I was like, maybe this is not the chimney, but the intake of oxygen. Perfect, I continue. So ignition. Exactly the same, following the trend of what Sarah has told you about ignition of flaming. We also care a lot about smoldering ignition. So once upon a time, you have the sample, and it's not burning, it's very safe in the lab. What do I have to do to make it burn? Well, what you have to do is you have to bring an ignition source. What we do typically is we bring a coil. A coil we power up, and the coil gets really hot, ohmic losses, and then we burn into the pit, and it works fantastic. If the pit is in conditions to sustain a smoldering, we always ignite. But the question is it going to move away from the ignition source? And what we discovered ourselves, and it was discovered also by Dr. Franzen in the 80s, this plot over here, which is a little of a mess, I'm going to show it to you, is that only pit samples that are here can ignite, and the pit samples that are here cannot ignite. Franzen could not ignite, we could not ignite, so we agree on this. We did this experimentally and numerically. This curve over here is computational. Those black dots are Franzen's experiments, and this axis this is the moisture content in dry base, and this is the inorganic content in dry base. Right? So when it's pure carbon, and it has absolutely no water, it's very dry, it's a piece of cake to ignite. Now, as you start to increase the amount of inner content, that could be called the sand or the ash, now there is a point past 80% that you have difficulties igniting it. For example, we were sent soil from the Andes, where they have been seen smoldering fires, and they were, what is this? And it was a very inorganic content. It was not called peat, because if it doesn't have more than 50% carbon content, an ecologist cannot call it peat. They say, well, okay, what is it? An isosoil. So it's a soil that was very high in organic content, and it just sometimes wanted to ignite, sometimes they don't want to ignite, right? And if it's even above 80, then forget about it. You're not going to ignite it, although it has some organic content. And the same with water. The same with water is there is a point where actually it cannot ignite, or if it ignites, it will not self-sustain. We call it critical moisture for ignition or critical moisture for extinction. And it's in peat, which is very porous. Peat can have inside more water in mass than organic material and still burn. So this is a freaky material in that sense, right? You could be at 150. We burn peat at 150. 150 says that it has the same amount of water in mass as peat and 50% on top, and it still is able to smolder. Now, it was not fast smoldering, high intense. Satellite definitely cannot see it, but it was self-sustaining. It was able to propagate across our sample after ignition. So when you look into the soil, this applies to all fuels in principle, is can this ignite? The first thing that, you have to look into all things. You have to look into a specific heat, you have to look into the conductivity, the thickness, the density. But in smoldering, the first two questions that have to come into mind first is how much water does it have? And natural fuels have a wide range of water content. And the second one is what is the inorganic content? And once you have that, you can put it into this map and might be able to smell. Then a little bit on work on fire brands. I believe that Alex Filkov told you everything about wildfires in the urban interface, and later on today, Michael Gorner is going to tell you everything about fire brands. I want to highlight my specific view on this. These are experiments done at Berkeley. I have a bias. I did my PhD there. They have an apparatus that looks like a fish, a little tunnel. They have a fuel bed, and they drop hot things on top. It's a lot of fun, seriously. Typically, they were metal beads because of power lines creating sparks and melted solids falling. But it also relates to the arrival of a firebrand into a fuel that is either in the forest or in the wild urban interface. And they have nice flow, and they have a camera, and they can look into this. It was known, but what they discovered uncontroversially is that they took these embers and they varied their temperature and their size. This is very nice when you do it with metal, right? It's much more difficult with actual fuel. And then they were tracking of when they had ignition. And what they discovered two very separated lines. This one is when you cross this line, there was smoldering ignition. So here, there is only smoldering ignition. And when you cross this line, in this corner, they were having flaming ignition. So they're very different. Some fuels might have them closer by. But in this case, they're very different, very clearly separated. And you are able to do smoldering with much smaller diameter embers and much lower temperatures than in flaming. So when you see a plot like this, it makes the point that it is easier to initiate a smoldering than it is to initiate a flaming. With the caveat that once you initiate a smoldering and you remove the ember, you literally throw it away, this might continue to smolder and transition to flaming an hour, a day, a week afterwards. And then people will say, no, it was not a smoldering, it was flaming. I saw the flames. Because they were not looking when it was smoldering, right? So this is one of the big misunderstandings of smoldering, that the people only look when the flames appear. Therefore, what was happening before it doesn't get this close. And then we have self-heating. I alluded to this very quickly. Beautiful Nobel Prize, Semenov, thermal ignition. It's all about combustion fundamentals, but Semenov theory can be applied to self-heating ignition, which is one of the ways how smoldering can be initiated. It pretty much says you have different temperatures in your system. The system is reactive, and this is the power that it is released by the chemical reactions. It's a curve in red, or by heat losses, it's taken away, it's a line, it's in blue. And you have points of equilibrium. This point, there is as much being generated as it is being lost. It's a point of equilibrium, and it's stable. The system loves to be there, and it will stay there if you let it. And there is another point of equilibrium. This one is unstable. In this point, there is exactly the same amount of energy being released by the chemical reactions, now by heat losses, but it's unstable. If you move it a little bit to lower temperatures, it will go to this one. And what happens if you move it a little bit to higher temperatures? It goes up and will never come back again. Thermal runaway. This now, everybody's talking about thermal runaway because of lithium-ion batteries, because they do thermal runaway. What unfortunately people in batteries are not saying is that this actually becomes to the fundamentals of combustion theory, even a Nobel Prize, and thermal runaway is how we understand ignition. And then Frank Kamenetsky came afterwards and showed, well, even if the system is thick, a pile of fuel is thick, so Semenov doesn't apply, and the smoldering might happen in the center, so you have a role for conduction heat transfer, and Frank Kamenetsky has that. So we did experiments in the oven. We put peat in the oven, we close the door, and we just watch for hours and hours and hours, sometimes even days, to see what was happening. And if nothing was happening, this is the temperature of the oven. This is we put thermocouples in the sample. If nothing was happening, we start the experiment again, and we increase the temperature until what we see is that this is the oven temperature. This is a sample inside an oven at 145 Celsius, and this is the temperature of the sample. It went above the temperature of the oven. How can the peat go above the temperature of the oven? The oven, if you are doing food in the kitchen, is the source of heat. How can anything, my pizza, etc., can go above the temperature of the oven? Because you are having combustion reaction. People over, I don't see a flame. Don't look for a flame because you are having heterogeneous chemistry. You are having char oxidation and smoldering combustion. And actually it can go and ignite. And then when we saw these results, we see peat can self-ignite. I find it fascinating. It's a breakthrough. People say, Guillermo, the oven was at 145 Celsius. Have you seen this often in the planet Earth? I thought, actually, you have a point. So what we do is we use Frank Kamenetsky theory. Frank Kamenetsky was a student of Semenov. So we are using Semenov theory, which got a Nobel Prize, to extrapolate to different sizes and different inner contents. So different sizes. For example, this is an oven that fits into a lab, so it's a small sample. Our biggest sample, I think it was 20 centimeters. It's very small. But with Frank Kamenetsky, we can say, what would happen if it were to be a cube of a meter? What if it will be a cube or a slab of 20 meters? Peat can actually be of 20 meters. Peat can actually be 50 meters. The water table might be in the middle, though. So now what we are able to say is that self-heating can happen here, actually. Self-heating at temperatures below 40 Celsius, that's temperatures that are possible in the planet Earth. Obviously, this is more closer to Spain than it is to London. It is true, right? London, it will be more like here, over here. So London self-heating doesn't happen very often. In Spain, self-heating can actually happen. It's one of the reasons why we have deserts. Because if there is any vegetation in such a dry place, exposed to oxygen, it will just burn. Not with flames, it will just slowly cook by itself, by self-heating. And this curve tells you that self-heating, it is possible, right? I just bring you this because not often we have an opportunity in current far science to talk about self-heating theory, and I absolutely love it. And then if you have smoldering, you can actually, if you have self-heating, you can have smoldering. These are experiments that we simulated in the computer. The experiments were done at WPI by Ali Rangala. This is the temperature, different times, an hour, 70 minutes, and 80 minutes. This is the reaction rate. We love this, computationalists. Reaction rate. And this is the oxygen concentration. And it's a wedge. It was actually a pyramid, inverted pyramid of coal. The walls of the wedge are hot, okay? And what the experiments of WPI were showing is that there was self-heating, ignition, just by the heat of the walls. And instead of being in the hottest place, which was here, the ignition was happening here. So they published a beautiful paper in Combustion and Flame saying, this is freaky, guys, because something is happening. Instead of the self-heating happening in the hottest place, they're happening at some distance from here. And what we thought is, like Ali Rangala, I think you have a point, it ignited at the point, but you could only detect it once it had moved forward to actually looking for oxygen concentration. So what you see over here is that how the hotspot develops close to the center, and it starts to propagate. That's propagation, that's not ignition. Now it's propagation spread. And how blue is that is short of oxygen. It doesn't have oxygen in the peak. It's the hottest, but it doesn't have oxygen, and it moves towards the oxygen. And that is a way of explaining it was not just ignition. It was ignition and spread of smoldering. That's why we did this work, right? To make the point that self-heating and smoldering are actually interlinked. Now, a spread by itself. I want to show you these experiments over here, which are, we have a lot of fun. Actually, the experiments were done by Rory Haddon. So these are the same setup that I showed you before, seen from the top. It's about 20 by 20. Now what we did is we altered the moisture of the peat. So this is a slope, this is a strip of wet peat, and this is dry, and this is a checkerboard of wet, dry, wet, dry, wet, dry, wet, dry. And what you can see, how dramatic the moisture content is in the spread rate. So it always ignites, but obviously it moves much faster if it's dry than if it's wet. So when you look into the structure of the front, and this is something that I have alluded already, this is the typical box that we do experiments. The fire is propagating in this direction, the smoldering is propagating in this direction. If you move to here, this peat has absolutely no idea for the next 5 hours that anything is happening in this very boring lab. Right? As you move closer, this peat starts to say, something is happening. It's a little bit warm. There is this warmth that is coming through radiation through the pores, conduction of the fibers, and a little bit of the convection of the air. And then when you're closer, this actually says, I lost my water, I've been preheated so much, I'm dry. And then it's like, I am decomposing, pyrolysis, and I'm leaving behind char, and then the char burns, releases heat, and drives the process. So this is how we like to look into time and depth of the smoldering. The smoldering is propagating downwards. Obviously, in 2D satellite, we are seeing this as a process that is only propagating laterally. But if you were to look into the other side, more like the view of the experimentalists in the lab, you see the depth, and you see how the peat starts to be lost at the surface, but at the bottom there is still peat, and then you have dry, paralyzed, and you have the ash that is left. And at the end of the experiment, you are left with ash. Where is the peat? It's in the atmosphere of London. That's what it is. So this is experimentally, numerically can show you this, but I don't want to dwell too much into this. Then smoldering, because it's three-dimensional. From the satellite, we see it 2D, but if you're on the side, you can see the third dimension is three-dimensional. You have lateral spread, and this drawing over here is showing you how the heat is propagating, the drying is propagating in 2 directions, but we call that lateral spread. And the lateral spread in smoldering produces what is called the overhang, which I want to highlight because for a while they thought it was fascinating and ecologists were observing the overhang. The overhang is why if you see a smoldering fire, you should not do like this. Because you could, and it has happened, be on the overhang, and cars, trees, people, houses have been lost because of the overhang. The overhang forms is because smoldering likes to burn better, faster, slightly below. And then it creates an overhang, and then the overhang collapses. And then the overhang burns. It's dry peat that falls into the ash, and it creates a conflagration. That will be the word. It actually sometimes even flames. Then it disappears, and it continues. And the overhang is fascinating because why would peat want to burn faster, a little bit deeper? Why is it shy from the surface? And literally there is an optimal depth for smoldering where it can still get enough oxygen, but the heat losses have been reduced. So overhangs is a telltale that smoldering is happening. Flaming doesn't do overhang. And then we have the lateral in-depth spread, vertical. This is something I want to highlight. As we increase the moisture of the peat, it's more difficult to ignite. And in general, it spreads slower, with the exception of vertical spread that can actually be accelerated when you increase the moisture. So this is the moisture content, okay? And this is spread rate, not lateral, this is spread rate. And in circles that are empty, this one over here, is the downward spread. So, and in circles that are, squares that are filled, is the lateral spread. So lateral spread goes down, even to extinction at a critical moisture as the moisture increases. Everybody's expecting that. I've even mentioned it to you today. But look what happens with the in-depth spread. It goes up. It actually ends up also extinguishing itself, but it goes up. Why have you ever seen a phenomena that accelerates with moisture? I was convinced Xinjiang did the experiment wrong. And I sent him back to the lab. Some of you might have seen Xinjiang Juan. I sent him back to the lab because there is no way we are publishing a paper saying that moisture content is increasing the spread rate. He convinced me. And I thought, well, we don't know what is happening, but this is actually something that can be observed in the lab repeatedly. Then, with a computer model, with GPyro of Chris, we were able to replicate this. And then we can use GPyro to say, what the hell is happening here? How can you accelerate the spread with moisture content? And what happens is peat, being a natural material, when it has a lot of water, it expands. I don't know if you have experience with this. You take peat, you put water, you leave, you come back a few days later, and the peat has expanded, right? It has the moisture content, but it has just swelled up, right? So when it swells up, and then the smoldering dries it very quickly, within days instead of weeks, it leaves massive pores. Now they don't have anything, they don't have water. And the pores means that smoldering doesn't have to travel through the peat. It can actually quickly move around the pore and accelerates the spread. So this is one unusual but confirmed mechanism where the presence of moisture and the swelling of the porous media will accelerate the spread rate. And good, just want to finish soon. The depth of burn, fine, you're experts on this, and going up. Emissions, this is an important thing, and I think I will finish with emissions. Emissions is a big deal. This is the beautiful city of Singapore, the Marina Bay, on a beautiful day. Actually, I was there. Okay, I love it. This is the same place when there is haze. You've seen haze. You've heard of haze. It's in the news. They have no idea what it is, but people are suffering, and it's in the news, and they call it haze. Just to note that my research lab is called Haze Lab, because we look into the origins of haze. And these are the smoldering fires of Indonesia and Malaysia that created this cloud. It doesn't go up and it goes into China. It actually stays on the ground and it moves at the mercy of the winds. And in this case, Singapore was in the path of this cloud. It's not a cloud. It's of this wind. And the haze stays there for weeks. And this is extremely, extremely poor air quality. No engine, no set of fleets in the planet Earth has been able to do something like this of this air quality. When you look into the emissions, doctors faint. This is particle matter 2.5. 2.5 microns can go into our lungs and start to go deep into our blood system. If they were to be actually one particle micron actually go into the brain. This is what the cars can do in Indonesia, in Singapore, and this is what happens in haze. It happens about every 3 to 4 years. We're due one this year. And this is what they breathe, not when they go into the street and not for a few days. This is what they breathe. They don't have other airs. This is the air they have. This is what goes into the houses. This is what goes into the classrooms. They goes into the sport facilities, and they breathe these babies and elderly and older people breathe during days. It's extremely dramatic. You can see that the emergencies, cardiovascular and respiratory emergencies, when there is haze, go up the roof in the region. You can actually tell the arrival of haze, not just by looking to the window or smelling it, because you see hospitals suddenly happening. What is happening with all these people, their lungs and the cardiovascular systems? Why is this happening? Because smoldering is incomplete combustion. It actually, all pyrolysis, all these pyrolysates, they go straight into the smoke. They don't get involved at all into the process of combustion. They are released as they are. So there is an incredible amount of CO, way more CO. There is a lot of particle matter, which actually is released in the form of droplets. There is a lot of methane. There is a lot of all these hydrocarbons, very complex. I'm not a chemist. All these will be obliterated by the flame, and the energy will be released, and there will be traces. This will be 0.04. This will be 0.01. This will be like, oh, we have a lot of CO. We have like 50. Right? Grams per kilogram. Smoldering multiplies all these. They're not traces anymore. They are abundant in the smoke. And all of them have different effects upon finding life and humans. Just an example of the chemistry, typically the CO to CO2 ratio. This is an experiment where we let the peat flame. Peat doesn't like to flame, but if you insist, it allows you to flame. If it flames, you can see the CO to CO ratio goes into the typical ratio that you find in all flames, even if you burn a plastic. It is this range specifically of CO2-CO ratio, but at the same pit you smolder it, and it goes, the CO2-CO2 ratio goes up the roof because there is way more CO and unburned hydrocarbons and pyrolysates per amount of CO2 that is the material, the carbon that truly was oxidized. When you look into and you filter, now it's not the gases, now the particles. This is a very concern for respiratory illnesses. You put filters, right? So you filter the flames smoke, you filter the smoldering smoke. You just look at the filters, right? This is if it's flame, right? It's trapping tiny amounts of soot. These are 2.5, and these are 2.5 PMs, and this is 10 PMs. And this is what happens with smoldering. Smoldering at the beginning and smoldering at the end. So just by looking into this, you don't have to call a chemist to do the analysis for you. You already identify there is an incredible amount of particle matter at the smoldering stage, way more than it is in the flaming, and there is no soot. And this is important because we combustion scientists love soot. It's very complex, it drives radiation, but it only happens in flames. And then we can look into what happens if the pit fire is in the tropical region, on the boreal region. And although this emphasis today, I'm bringing it for pit fires, this applies to all emissions from smoldering, even smoldering of synthetic materials in a built environment. I'm gonna finish, almost on time. I just want to show you a video. So I'm an engineer, many of you are engineers. We don't do field trips, but once upon a time, we did something crazy. It was with Afi over there. We took the lab into the jungle. So we went to Indonesia. It was very safe because we were with Indonesians. That's absolutely essential. So they were taking care of us, but also there was a geoscientist that was taking care of engineers to make sure that there was no one lost in the jungle. And we wanted to observe a real smoldering fire, but not wait until the satellite sees there is a fire and then look, oh yeah, it's a smoldering. That's what many people do. We wanted to control the phenomena. We wanted to initiate the fire ourselves. People are looking at us like, what? We wanted to not only ignite it and go home, we wanted to ignite it and let it develop over the course of days and weeks. This is crazy, it has never been done. So what we did is we were able to ignite. The video is not gonna, yeah, this one it does, fantastic. So this is what we managed to, it was very safe, don't worry, I can tell you all about this. We did it properly. We managed to have the smoldering, it took us a while. It is smoldering, the pit is smoldering, and this is Indonesia on the dry season. This is the tropics. It rains more than in London in the dry season. So I just don't want to think what happens in the wet season in Indonesia. And this was a torrential rain. I don't know if you can see, these are the drops of water falling from the paraguas, the umbrella, the umbrella that we have ourselves. It was pouring rain for 15 minutes. So it's like, okay, guys, let's go home, take the flight to London. The rain has completely destroyed our experiment. We have to leave a week later, sooner. No. This was a joke for smoldering. Smoldering continued under the tropical rain. Not only this one, there was another one where, like, okay, that's it, that's the end. It collapsed our tent. It actually made us have to run to our headquarters. The smoldering continued thereafter. It just could not be stopped by these rains. That's why in Indonesia, you need the wet season. I just don't want to know what happens in the wet season in Indonesia. The wet season stops smoldering fires in Indonesia. The dry season cannot stop the smoldering fires in Indonesia. Okay? So this is us. It was an incredible amount. One of the highlights of my career. I don't think I will be able to do it again. I don't have energy. And it was amazing. And the whole team came back alive. I'm really happy about that. And this is the crazy things that we did. Good. So I just finished. I just want to tell you that smoldering is a threat. As an engineer, I care about protection, so I care about stopping bad fires. At the same time, that means that I would love to promote good fires as well. But it's a threat to property, to humans, and to the environment. Smoldering is the most persistent. I think I was convincing, hopefully, with the science about this. It's easier to ignite it, and it's more difficult to suppress. So there is something going on with the smoldering and humanity and the planet Earth, that if the simplest step, the simplest chemistry, you can go to, I think someone has gone to 15. I've not been more than 9 steps, and I love it. You're like, what? But at least you have to have 2 steps, because you at least have to have the pyrolysis that produces the char, and then you can actually do the oxidation of char. You can go more complex, and you will be very welcome, but you cannot go less complex. I'm very sorry that such a thing as 1-step smoldering doesn't exist. You might fiddle with it and have a lot of fun, but scientifically speaking, there is an issue there. that these are the largest fires on Earth. I don't know if I mentioned this to you. What do you mean, Guillermo? It's not the largest acres. No, it's not. It's not the fastest flames. No, it's not. It's not the highest heat release rate. No, it's not. So what is it? Why do you say it's the largest? It's the largest fuel consumption per unit area. But not by 1.5, but between 10 to 100 times more fuel. So the satellite sees a fire, and it matters if it was smoldering or if it was flaming, because you need to multiply that acreage by 100 or by 1, depending on what type of smoldering of combustion was happening. When you sum, no one has done this, but when you try to sum up all the footprints of all the smoldering fires known to humans, and we only know a small fraction of it, we see that they release carbon to the atmosphere in the order of the amount of carbon that is released by the worldwide fleet of cars. Now, that is sizable in the sense that something that we humans have something to do with, wildfires and smoldering, has, in terms of emissions to the planet, the same size as the number one worry that we have, which is our civilization having an effect on this. And this carbon is not fossil, so it's not us bringing it back. It has a component that is natural, but it's all fossil. Sorry, it's all carbon in the sense that it takes 100 to 1,000 years for nature to store this carbon in pit again. I do think that smoldering is an emerging topic in science, and there is so much to be done ahead of us. This is just scratching the surface. This is the top of the iceberg peak in terms of all the things that we don't know and that we would like to know. So hopefully I've convinced you of the importance of smoldering in wildfires. And when you hear someone saying it's not burning, it's not a fire, it's just smoking, you send these people to me, please. Thank you.